Hey chemistry crew, Mr. Collier here. Today I want to go over pages 20 to 21 in the gases packet, which is about the ideal gas law. So the first thing to mention is that the ideal gas law, which is written as PV equals nRT, is an equation that looks at a snapshot of a single gas. Our previous equations look at kind of a before and after for gases, like what happens if I change the pressure or the temperature or the volume. Here we're looking at what if I know some, but not all of the things about a particular gas at a particular point in time. One of the big things that it includes that our previous equations did not is the actual number of particles, the number of moles of that gas that you have. That's that N. The other thing it includes is a gas constant, because one of the things we looked at in all the Boyle's law and Charles' law is that as you change these variables, they change consistently. That's because there's a constant relationship between these gases, and that's what this R value is. It is the gas constant, and it has a value, 0.0821, but it also has units that go with it. And those units dictate what all of the units in this particular equation are going to be. We need to use atmospheres for pressure, liters for volume, moles for the number of particles, and Kelvin for the temperature. Once we use those, it's as simple as plugging values into this equation and solving. But because we have to use those particular units, there often are some conversions when you're doing problems. So let's take a look here. We go over these in the regular notes, so I don't know that I need to go over them right now, but look into that if you have any questions. There's a second video where I go over the notes. Same thing with this example problem. This example problem is from those notes. So let's jump down to the new stuff that you needed to do here, which is on page 21. So here, again, I rewrote the equation and the units to remind myself everything as I'm doing these problems, right? So question number 1 says, what pressure, right, so the P is going to be my unknown, is required to contain 0.23 moles in a 4.2 liter container at a temperature of 20. Now, one thing about this one that makes it not too bad is we already have moles and liters. So the only conversion we're going to need to do is that 20 Celsius needs to be in Kelvin. I'm going to add 273. My 0.0821 gets put in. All of my values get put in from up top. Notice I've got P, right? This is my volume, PV equals nRT. N is the moles, R is the constant, T is the temperature. Now I'm simply going to solve this algebraically and get my final answer. Since we're working with 2 significant digits in my lesser values here, we're going to round off to 2 significant digits. The answer is going to be in atmospheres, because that is the unit that this equation will spit out when you're done, because of the atmospheres in the R means that our final pressure will be in atmospheres. Couple more here. Also, note that this section in the packet, the answers are at the bottom of the page if you want to reference just did I get it right or not. All right. Oxygen is collected at a pressure of 123 kilopascals. So right there, we're going to need to do a conversion, right? So I'm going to go from kilopascals, divide it by how many kilopascals are in an atmosphere, and that converts it to atmospheres. Also, another thing I like to do, this particular question is asking me for the temperature, right? Sometimes I'll take the original equation, PV equals nRT, and I'll just arrange the equation before I even begin to be solved for the variable in question, in this case, temperature. That makes it a little easier for me, but some people like to use the original equation and then shuffle the numbers around. That's fine. So anyway, I've got my pressure now. I'm given the volume, and it's in the correct units, so no conversions needed there. I've got 0.5 moles of the gas, and I've got the gas constant. Now I've plugged those in and solve. That's going to spit out a temperature, but remember that temperature is going to be in Kelvin. So I'm going to subtract 273 to get it in Celsius. And the last problem here on page, again, 21, how many moles of chlorine gas? So I'm looking for moles, so I'm solving for N. So I went ahead and rewrote this equation to solve for N. That's my preference, but if you would rather leave it as PV equals nRT and then plug the numbers in and rearrange them, that's fine. I've got 100 kilopascals, so I'm going to simply turn that into atmospheres. That's where this number here came from, was me converting that to atmospheres. I've got my volume in liters, so no conversion necessary. I've got my temperature in Celsius, so I'm going to add 273 to make it Kelvin, and I've got my gas constant. When I do that, it's going to spit out a number of moles. That's my number of moles. However, it says after determining the number of moles, calculate the number of grams. So now I'm going to multiply by the molar mass, 71 grams per mole for chlorine. I just used that molar mass, which we haven't used much in this chapter, so you might have to go freshen up on that. And that spits out how many grams, right? If there's 71 grams in a mole and I've got a little over a mole, I'm going to have a little over 70 grams. All right, that's it for pages 20 and 21. Let me know if you have any questions.